So my friend, this is one of the question which came in GATE 2020 forenoon session from fluid mechanics subject. This question belongs to the chapter hydrostatic forces. Let us read the question. The barrier shown is placed in a tank of unit width in bracket 1 meter into the plane of the screen is modeled as cantilever. So my friends, please observe, I am having a barrier which is placed in a tank, and it is given that the width of the tank is 1 meter and this barrier is behaving as cantilever, where at the bottom the edge is fixed, bottom part is fixed, and this top part is free. Now let us read further. The maximum absolute bending moment developed in the cantilever is dash kilonewton per meter. So he is asking what is the maximum amount of bending moment is developed in this cantilever. Density is given as 1000 kg per meter cube. So let me assume we are having water on this left part and right part. G value is given as 10 meter per second square. Now the question is how to approach this problem. So he is asking bending moment, my friends. What is the meaning of bending moment? We should know the force and we should know the perpendicular distance. Now please try to understand, the water which I am having on the left side and right side, they will be applying the uniformly varying load. Now in hydrostatic forces chapter, we have seen how to convert this uniformly varying load applied by the liquid into point load, and the formula was given as Fp is equal to rho g h bar into area, where h bar was the depth of centroid from the free surface. So using this formula, we will be getting the point loads acting on the left face of the barrier by this left side water, acting on the right face of the barrier by this right side of the water. Okay. Now how to find the point of application? How to find this perpendicular distance? For that we can use this formula, my friends. H star is equal to h bar plus Ixxc sine square theta upon Ah bar, where H star is the depth of center of pressure from the free surface. Now in one of the special case we have seen, if the surface, plane surface is vertical plane surface, and if it is touching the free surface, then after solving this particular factor we will be getting the 2d by 3, where d is the depth of the surface, plane vertical surface. So let us see, my friends, let us solve, let us try to understand what will be the point load acting on the left face of the barrier by this left side water. So let me say FL is the force applied by, applied by this left side water on this left face of the barrier, and let me assume the depth of the water in left side of the tank is HL. So basically I am assuming HL is equal to 4 meter. So what will be the value of FL? Rho G H bar. What is H bar? HL by 2. What will be the area? Area will be HL into 1 meter. So HL into 1. So if you observe, if I solve a little bit, rho g HL by 2 into HL into 1, it will be, on simplification, it will be giving me half rho g HL square. Okay. Now similarly, if I try to observe, if I try to calculate what will be the hydrostatic force exerted by this right side water on this right face of the barrier, so let me say it is Fr, and let me say this is basically Hr. So similarly, what are we going to get? Fr will be equal to, in the same way if we solve, half rho g Hr square. So these are the magnitudes of point load acting on this barrier which is modeled as cantilever. So one part of the problem is done. Now I need perpendicular distance. So let me say, my friends, this distance is HL star. Depth of the center of pressure from the free surface for this left side water. Similarly, let me say here basically, let me say this is HR star. Now then what will be the value of HL star, my friends? What will be the value of HL star? We know 2D by 3 na. So HL star will be equal to 2HL by 3, 2HL by 3, and HR star will be equal to 2HR by 3. So these are the distances from the free surface. Now let me say, look at here my friend, this part is fixed surface na, this part is fixed. So let me take the moment about this. Let me take the moment about this. Let me say it is point O. So let me taking movement about O. So let me try to do one thing. Let me say the clockwise movement is positive. Let me say clockwise movement is positive and anti-clockwise movement is negative. So look at here my friends, what will be the net movement? What will be the net movement? Look at here, the clockwise movement is positive. What will be the net movement? Let us try to find out the moment of this FL force. So force FL into perpendicular distance from O. So look at here my friend, this total is HL, this is HL star. So the perpendicular distance will be HL minus HL star. So FL into HL minus HL star. I am taking it positive because the moment applied by this force FL will be clockwise. Now let us see what will be the moment applied by this force FR. It will be FR into perpendicular distance. What will be the perpendicular distance my friend? This total distance is HR, this is H star. So this perpendicular distance will be HR minus HR star. Now the moment applied by this force FR will be anti-clockwise, so I am taking it as negative. Now look at here, substitute the values my friends. FL is half rho G HL square, HL minus HL star, HL minus 2HL by 3. So HL minus 2HL by 3 will be giving us HL by 3 minus. Let us substitute the value of FR my friends. FR is half rho G HR square. Now HR minus HR star, HR minus 2HR by 3 will be giving us HR by 3 only. So if you solve little bit, you will be getting 1 by 6 rho G HL cube minus 1 by 6 rho G HR cube. So if I take 1 by 6 common my friends, look at here, if I take 1 by 6 rho G common, what I am going to get is HL cube minus HR cube. Let us substitute the values my friends. Let us substitute the values. 1 by 6 into 1000 into 10. What is the value of HL? HL is equal to 4 meter. What is the value of HR? HR is equal to 1 meter. So 4 cube minus 1 cube. Now my friends, what is the 4 cube? 64. 64 minus 1, 63. 4 cube is 64. Minus 1 cube is 1, you will be getting 63. So now if you cancel 6 and 63, around 10.5 will come. So 10.5 into 10 will be 105, and if I take this 1000 in kilonewton form, so net movement will be 105 kilonewton meter. This is the answer my friends. This is the maximum absolute bending moment developed in the cantilever. Thank you. Hello friends, this is one of the question which came from fluid mechanics, fluid kinematics chapter. So let us read the problem. The velocity field of an incompressible flow. So please observe, in question they have given incompressible flow. The velocity field of an incompressible flow in a Cartesian system is represented by. So the velocity vector is given 2 in bracket x square minus y square I cap plus small v j cap plus 3 k cap. He is asking which one of the following expression is valid for small v. So he is asking what is the expression for this small v. So look at here, my friends, how to proceed this problem. As we know, for incompressible flow, divergence of velocity vector will be 0. Now what is the divergence of velocity vector? Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So what is u? U is this part. Of course, a small v is this one and this is w. So let us substitute over here. Very simple question, my friends. Dou by dou x u 2 x square minus y square plus dou by dou y of v. So basically dou v by dou y plus dou by dou z of small w. How much is small w, my friends? 3 constant is equal to 0. So my friend, let us see, this 2 will come out of the partial differentiation. So the partial differentiation of x square with respect to x will be 2x, partial differentiation of y square with respect to x will be 0 plus dou v by dou y, partial differentiation of 3 with respect to z will be 0 is equal to 0. So my friends, 2 into 2 will be 4x, 2 into 2x will be 4x. So basically what I am getting now, dou v by dou y is equal to 4x. Let me bring it to the right hand side, minus 4x. So let us integrate with respect to y. Let us see what are we getting. V is equal to minus 4xy plus some arbitrary constant will come, which will be the function of, I am doing the partial difference with respect to y now, my friends. So the arbitrary constant will be the function of x comma z. So let us see which option is matching, my friends. Look at here, option 1 minus 4xy, and the function of x comma z is given as minus 4xz. So basically this is our right option, my friends. Option 1 is the correct option. So my friends, here in question it's very simple. The only thing which we need to know, that if a flow is incompressible flow, then the divergence of velocity vector will be 0. Here I want to add one more point, my friends. Let us suppose if he is giving irrotational flow, then you know for irrotational flow the curl of velocity vector must be null vector. Okay, so if that change is coming, please note that. Thank you so much, my friend. Thank you. So my friends, let us continue the discussion on previous gate questions. So this is one of the question which came in gate 2020 mechanical forenoon session. This question belongs to fluid mechanics. Let us read the question. Air discharges steadily through a horizontal nozzle and impinges on a stationary vertical plate as shown in the figure. So my friends, you can observe we are having one horizontal nozzle and we are having a vertical plate, and air is impinging on this vertical plate at point O. So let us read the further data. The inlet and outlet areas of the nozzle are 0.1 meter square and 0.002 meter square respectively. So this inlet area is given 0.1 meter square, this outlet area is given 0.02 meter square. Take air density as constant and equal to 1.2 kg per meter cube. So air density is given constant, which means they are saying the flow is incompressible flow. If the inlet gas pressure of air is 0.36 kilopascal, so here at the inlet gas pressure is given 0.36 kilopascal. The gas pressure at point O on the plate is dash kilopascal. Here he is asking the gas pressure. So my friends, how to solve this problem, how to approach this problem? So look at here, let me say this is point number 1, this is point number 2, this is point number 3. So basically he is asking the gas pressure at point number 3. So look at here my friends, already he has given steady flow and incompressible flow. So we are eligible to apply the continuity equation, which is AV is equal to constant. That means we can apply A1 V1 is equal to A2 V2. So how to solve this problem my friends? We will do one thing. First we will be applying the Bernoulli's equation between 1 and 2, and then further again we will be applying the Bernoulli's equation between 2 and 3 to find this Pg3. So my friends, I will be solving this problem in the simplest way without using calculator. So look at here my friends, let us suppose if I am applying the continuity equation between 1 and 2, so let us see what can we write. Please observe my friends. For study and incompressible flow, my friends, we can write area into average velocity is constant. So of course A1 V1 is equal to A2 V2. So my friends, A1 is given as 0.1 meter square, 0.1 meter square, 0.1 V1 is equal to A2. A2 is given as 0.02 meter square. So 0.02 meter square into V2. So from here we can easily observe V2 is coming 5 times of V1. Fine. So the velocity of the air at the outlet of the nozzle is 5 times of the average velocity of the air at the inlet of the nozzle. Now my friends, here you must remember, already we have discussed in class the shortcuts for applying Bernoulli's equation. If the potential heads are same between 2 points, then the shortcut which I have given you was P1 minus P2 is equal to half rho V2 square minus V1 square. So we will be using those shortcuts over here to solve this problem in simplest and quickest way. So look at here my friends, I am writing the statement for you people, please observe. Applying Bernoulli's equation between 1 and 2 for same potential head, So my friends, Bernoulli's equation shortcut form is basically P1 minus P2 will be equal to half rho V2 square minus V1 square. Now look at here my friends, P1 is already given to us and P2 is PATM. So if I substitute here, I will be getting the gas pressure at 1, absolute pressure minus atmospheric pressure will be giving me the gas pressure. So Pg1, gas pressure at 1 is equal to half rho. Now my friends, just now we have seen from continuity equation V2 is 5 times of V1. So V2 square will be 25 V1 square. So 25 V1 square minus V1 square will be giving us 24 V1 square. So let me say my friend, this is equation number A. Now look at here. Look at here, my friends. Look at here. Let us focus at this point, point number 3. At point number 3, the velocity of air will be 0. The velocity of air will be 0, and I'm assuming the air is retarding to 0 velocity isentropically. So basically what I'm trying to assume is this point number 3 is behaving as a stagnation point. Stagnation point. So if it is behaving as a stagnation point, I'm free to apply the Bernoulli's equation between point number 2 and point number 3. Again, we can observe point 2 and point 3 are having same potential heads. So look at here, my friends. Look at here, I am writing, please observe. I am writing applying Bernoulli's equation between 2 and 3 for same potential head. So my friends, what are we going to get? Please observe. P2 minus P3 is equal to half rho V3 square minus V2 square. Now look at here, my friends. P2 is PATM. P3. So basically this will become minus PG3 minus gas pressure at 3 is equal to half rho. My friend, this V3 already we know 3 point is behaving as a stagnation point, so the velocity here is 0. So minus V2 square. So minus V2 square means what? Minus V2 square. V2 is 5 times of V1. So minus 25 V1 square. So basically if you observe, we are getting Pg3 is equal to half rho into 25 V1 square, my friends. Let us suppose this is equation number B. Let us do one thing, my friends. Equation 2, that is equation B, basically equation B divided by equation A. So what are we getting? Pg3 divided by Pg1 is equal to half rho into 25 V1 square divided by half rho into 24 V1 square. So my friends, if you observe carefully, this half row will be getting cancelled. V1 square will be getting cancelled. So Pg3 will be 25 divided by 24 times of Pg1, and this Pg1 is already given in the question. So let us substitute, my friends. Pg3 is equal to 25 divided by 24 into Pg1 is how much, my friends? Pg1 is 0.36. So look at here, my friends. 12 to the 24. Here I will be getting 0.03. So 25 into 0.03 will be 0.75 divided by 2. So basically, my friends, Pg3 is coming equal to 0.375 kilopascal. This is the answer, my friends. This is the answer, 0.375. Look at here. No use of calculator. Just what have we done? We framed two equations, and finally it is coming in this form. Pg3 is equal to 25 by 24 Pg1. Look, in exam we have to minimize the use of calculator. We have to make sure that we are doing minimum calculations. So look, already I have told you in class, whenever we are having same potential head, P1 minus P2 is equal to half rho V2 square minus V1 square. It is becoming very simple. There is nothing in the question. Pg3 is equal to 0.375. That is the answer, my friends. Thank you so much. So, my friend, this is one of the question which came in GATE 2020 mechanical forenoon session from fluid mechanics subject, laminar flow through pipe chapter. So, let us read the problem. Consider steady, viscous, fully developed flow of a fluid through a circular pipe of internal diameter capital D. So, we are having a pipe. The diameter of the pipe is given as capital D, and through this pipe a fluid is flowing which is having a steady, viscous and fully developed flow. We know that the velocity profile forms a paraboloid. So, you can observe in 3D, this is parabola in 2D, but if you see in 3D it will be paraboloid. So, the velocity profile forms a paraboloid about the pipe center line given by, so the velocity profile is given V is equal to minus C small r square minus D square by 4. Okay, meter per second, where C is constant. The rate of kinetic energy in joule per second at the control surface AB. Look at here, this is the control volume. He is asking at AB the rate of kinetic energy as shown in the figure is proportional to D power n. So, diameter power n, the value of n is. So, my friends, let us see. If we see the side view, how the things will look like. So, if we see in side view, we will be seeing a circle which is having diameter capital D. Let me say this is the center. Okay, he is asking kinetic energy rate, my friends. We know the formula of kinetic energy rate is half m dot into v square. Now the problem here is this v velocity is not constant, it is varying in radial direction. So we cannot apply the formula directly. So what to do? Let us take one small strip where we can assume the velocity is almost constant, and then with the help of that particular strip we will be finding the small kinetic energy rate passing through that small strip, and then we will be integrating throughout the pipe. So let us see, my friends, let us see. Let me say at a distance small r, let me say at a distance small r, I am assuming a thin circular strip of thickness dr. So let me say this is one small thin strip having thickness dr. So this is basically dr, my friends. Fine. So this strip is so small that I am assuming each and every fluid particle which is passing through this small strip is having almost same velocity. Okay, my friends. So what will be the area of this strip, my friends? The area of this strip will be 2 pi small r dr. My friends, what will be the small mass flow rate passing through this strip? Area we know. So look at here, del m dot small mass flow rate passing through this strip will be rho into small area 2 pi r dr into velocity. Let me write v. So this is the small mass flow rate which is passing through this small strip. So what will be the kinetic energy rate passing through this strip? So look at here, my friends, small kinetic energy rate passing through this small strip will be half del m dot into v square. So let us substitute the value of del m dot, my friends, half del m dot is equal to rho 2 pi r dr into v. V into v square will be v cube, my friends. If I substitute the value of v, small kinetic energy rate passing through this small strip will be half rho 2 pi r dr cube of v. So minus cube will be minus, c cube will be c cube, and I will be getting the cube of this small r square minus capital D square by 4 whole cube I will be getting. So minus, I am writing here minus c cube small r square minus capital D square by 4 whole cube. So my friend, this is the small mass flow rate which is passing through this small strip. So if I solve little further, dke dot will be equal to this 2 and 2 will be getting cancelled, minus rho pi c cube r, small r basically, small r square minus capital D square by 4 whole cube dr. Now my friends, if I want to find out the total kinetic energy rate passing through the cross section of the pipe, so how to find, my friends? I will integrate. So I will integrate. What will be the limit of integration, my friends? When small r is equal to 0, that is at the center, when small r is equal to half of the diameter, that is radius of the pipe. So look at here, my friends, what I am getting, 0 to d by 2 minus rho pi c cube r, small r square d square by 4 whole cube dr. My friend, these all are constant, I can take it out. So ke dot is equal to minus rho pi c cube 0 to capital D by 2 r. My friends, let us open this whole cube formula. So a minus b whole cube. So a cube minus b cube plus 3ab square minus 3a square b. So look at here, my friends, I am opening it for you. A cube, r square cube will be r power 6, a cube minus b cube, this is your b. So the b cube will be d power 6, 4 cube will be 64 plus 3a b square. So 3a small r square b square d power 4 divided by 16 minus 3a square b. So minus 3a square small r power 4 b d square by 4 dr. Let us multiply this small r inside, my friends. What are we getting? Ke dot is equal to minus rho pi c cube 0 to capital D by 2 small r power 7 minus small r, or you can write d power 6 divided by 64 small r plus 3 by 16 d power 4 small r cube minus 3 by 4 d square small r power 5 dr. Now my friends, if we integrate this small r power 7, we will be getting small r power 8 by 8. Similarly here also if you observe d power 6 divided by 64, the integration of r will be r square by 2. Here if you observe 3 by 16 d power 4, the integration of r cube will be r power 4 by 4. Minus 3 by 4 capital D square, the integration of small r power 5 will be small r power 6 divided by 6. And when I will substitute this limit, you can observe I will be getting d power 8. If I substitute the upper limit in place of small r, I will be getting d power 8. So from observation, I can write 100% kinetic energy rate will be directly proportional to d power 8. So my friend, the answer is the value of n is basically 8, my friends. Answer is 8. Thank you so much. My friend, this is the next question which came in GATE 2020 mechanical forenoon session, fluid mechanics subject, and if you see the chapter is dimensional analysis. Let us read the question. Froude number is the ratio of. So my friends, 4 options are given. So we know, my friends, already Froude number is the ratio of inertia forces to the gravity forces. Froude number. Very simple question, my friends, and already we have discussed in class. Generally the Froude number is used for the open channel flow analysis and all, where we are having free surface present. And my friends, if we see few other options, this option 3, if you observe, buoyancy forces to the viscous forces, this is basically your Grashof number, my friends. And you know, Grashof number is generally used for the analysis of free convection. My friends, if you see the fourth one, inertia forces to the viscous forces. My friend, this inertia forces to the viscous forces, you know, my friends, it's Reynolds number. And this Reynolds number is used for the analysis of viscous flows. Thank you so much. So, my friends, this is one of the question which came from hydraulic machines. Very simple question based on Kaplan turbine. So let us read the problem. For a Kaplan turbine, in bracket axial flow turbine, of course we know Kaplan turbine is basically axial flow turbine. The outlet blade velocity diagram at a section is shown in the figure. So at a particular section they have given this outlet blade velocity diagram. Here this CF is representing the flow velocity, CV is representing the blade velocity, and of course this CR is representing the relative velocity. So you need not to be confused, my friends. Already we know. Look at here. Don't be confused with the notations. We are representing this by VF2. We are representing this by U2, and we are representing this by VR2. Don't be confused. And of course this we are representing by beta 2. Don't be confused. The diameter at this section is 3 meter. So basically this velocity diagram, my friends, it is drawn at a section where the diameter is 3 meter. The hub, basically boss, the hub and tip diameters of the blade are 2 meter and 4 meter. So hub diameter is given, tip diameter is given. The water volume flow rate is 100 meter cube per second. So basically discharge is given. The rotational speed of the turbine is 300 rpm. So rotational speed is given. He is asking the blade outlet angle beta is in degrees, he is asking. So whatever the data is given, let us note it down, my friends. Look at here. Basically he has given the outlet velocity diagram at the diameter 3 meter. Hub diameter is given, my friends. So boss diameter is given basically 2 meter. Tip diameter D naught is given as 4 meter. Discharge is given as 100 meter cube per second, my friends. And rotational speed N is given as 300 rpm. He is asking basically beta 2 as per our notations. Okay, so how to find this beta 2? Look at here, very easy my friends. Look at here, if you revisit the classes, I must have told you this direction is basically tangential direction. This is basically tangential direction, and this one is basically your axial direction. So what will be the formula of tan beta 2 my friends? Tan beta 2, perpendicular divided by base. So what is the perpendicular? This VF2 is perpendicular my friend. This VF2 is perpendicular. What is base? This U2, small u2 is our base. Now the question is how to find this VF2 and how to find this base. So basically for finding this VF2 they have given discharge in question, and for finding this U2 they have given diameter and rotational speed in question. So look at here my friends, how are we going to find VF2? Finding of VF2, how to find this one? Look at here, discharge can be written as pi by 4 dO square minus dB square into VF2. So from here VF2 will be equal to 4 times discharge divided by pi dO square minus dB square my friends. Fine, VF2 is very easy to calculate. How to find U2? Very simple my friends. Look at here, for this U2, U2 is equal to what? Pi dN by 60. Pi dN by 60. Now it's very simple, just substitute this VFT and U2 over here, and then you take the tan inverse, will be getting beta 2. So let us substitute my friends, let us substitute tan beta 2. Tan beta 2 is equal to VF2 4Q divided by pi dO square minus dV square. Okay, U2 my friends, pi dN by 60. Pi dN by 60. Let us substitute the values my friends. Let us substitute the values. Tan beta 2 is equal to 4. Discharge is 100 into 60 divided by this pi, and this pi will become pi square my friends. dO square, dO is 4 square 16 minus dB square 2 square is 4. D is how much? 3. N is how much? 300. My friends, if you observe little bit of calculations, 20 is getting cancelled. Now look at here, 16 minus 4 is 12. 12 5s are 60. So what I'm getting my friends? Tan beta 2 is equal to 4 5s are 20 divided by 9 pi square. So basically if you want to find beta 2, tan inverse 20 divided by 9 pi square, and if you solve it my friends, beta 2 will be coming equal to 12.689 degree. So the answer is 12.689 degrees. My friends, if they are asking in single decimal place, then the answer will be 12.7 degrees. So very simple question my friends. The only thing you should know, how to calculate this VF2, for that discharge is given. How to calculate this U2, for this they have given diameter and RPM. Just substitute the values, you will be getting the answer my friends. Thank you so much. Thank you.